realize that when we shot those electrons through, even the double slit, if we had an instrument that was watching it pass through, it didn't make an interference pattern. It acted like matter, and it shot straight on the wall right as it came through the slit. We don't change anything else about that situation, and we just pull away the instrument and still watch what happens on the wall. It doesn't do that again. It turns into energy, and it behaves like energy. It goes out and it makes interference patterns. If you want to change the pattern that you see, if you're shooting electrons through a double slit, you see these interference patterns. The only way you can get an interference pattern is if something is behaving like a wave. That's it. Not if it's behaving like matter, only if it's behaving like a wave. To change what we see, all that you need to do is try to measure what's happening. The simple act of trying to measure what's happening changes what happens. It goes from an interference pattern to two distinct bands, as if you were shooting little marbles through, like it would matter. Okay? Now, as far as what was causing what was going on, okay, I'll get ready to start in a second. As far as what was causing what was going on, it's a mixture of both. See, what you got to realize is you can see an interference pattern because electrons have the ability to act like waves. You can see a straight band pattern because they also have the ability to act like matter. You've got to realize that this is simultaneously happening all around us. Don't hold them in. Just let it go. All of this is happening simultaneously around us. So if you're saying, like, if you're trying to limit that and say what is causing those bands, it's because they're leaping through orbitals. No. It's because whatever is causing those bands that we see is because those are electrons in the form of energy that are just acting like energy. When we try to view that electron, all of a sudden it becomes fixated as matter, and then we're not going to see those lines. So it's hard for me to answer because we've moved to the very abstract here. We're going in a place where you've got both things happening at the same time. If you are observing and you're trying to say that it's because electrons are jumping, well, then what you've done is, bam, collapse the wave function. Now it's back to matter, and those electrons are not anything that you're trying to measure and look at and say this electron's moving here. No, it's not, because then it's acting like matter if you do that. And if you stop everything and look at it, then it's not going to be like that anyways. I don't know. See, it's confusing for me to even try to explain. But it's like right here you sit, and everything that you see and all the matter that you perceived, you have collapsed the electrons down into matter. That's what you see. But at the same time, going on all around you, unbeknownst to you, because you are not technically observing it, there is also electrons acting as waves that are just becoming part of energy that someone else may be collapsing from another dimension, let's say, recognizing as matter. It gets way too deep. I like teaching this because it's just enough to make you think about it, make you wonder about it, but nowhere even have we scratched the surface in terms of the philosophy and the theory that could go behind this and what it means, like with the spiritual and all kinds of stuff like that. It's really cool stuff. All right, I'm ready. All right, so this brings us to what's called electron configurations. And what this is a way for us to write out what is happening in an easier fashion. Okay, you're going to use a set of numbers and letters to tell me how an atom is organized in terms of its electrons. For example, if this says H is 1s2, first of all, that's wrong. You might want to make a note of this so you don't get confused. That should actually read, I don't think this pen's working very well, but that should actually read, if I can squeeze it in, He. I didn't write it in the right spot. That should be helium, okay, instead of hydrogen. If I say helium is 1s2, what do you think that means? Huh? Okay. Good. That means, it means that I have one main energy level associated with helium. And in the first main energy level, the only shape, the only orbital that I have is the s orbital, which is spherical. So I have one layer, one shell, one principal number, shaped like a sphere, so we'll call it a S. And within that, there are two electrons. That's what 1s2 means. Okay? So if I switch and I say 1s2, 2s1, what does that mean? 1s2, 2s1. How many main levels do I have now? 2. I've only got 2 sublevels. I've got the 1s sublevel and then the 2s sublevel on top of that, right? I've got 2 electrons in the 1s, and I would have 1 electron in the 2s for a total of 3 electrons. So we're just building is what we're doing. And instead of trying to draw these 3-dimensional things out on paper, it will be way too time-consuming. We're just going to put it in number letter form and mean the same thing. Okay? We call this an electron configuration. Keep this in mind. Okay? Did I tell you that we already talked about this? I can't remember how many each one of these holds. Okay. Keep in mind that the S shape only holds 2, right? And the P, remember, it actually consists of 3 figure 8s stacked on each other. So it can hold, each one of those can hold 2. So that's why the P as a whole can hold 6 electrons. D, there are 5 shapes all superimposed on each other. So it can hold 5 times 2 is 10. F, since they're 7 shaped, can hold 14. Okay? So we keep that in mind because what we're going to look at is all the different atoms and how you can account for their electronic structure. Like if I say, take beryllium, how are the electrons arranged in beryllium? And you can figure it out by writing these electron configurations. Okay? Now you might think that that's not useful, but as we talked about in lab, valence electrons, that kind of stuff, this is a good way to figure out and keep track of valence electrons and explain in theory what is happening when 2 atoms come together. Okay? Okay, so we're going to be building up from the lowest energy. We're going to put electrons there. They're not going to start. Remember, the farther away we get, the more energy they have, right? So we're not going to have, if we only have 1 electron, it's not going to be way out here. It's going to be down here where there's low energy associated with it. Building up, Aufbau. In German, Aufbauen means to build up. Okay, so it's called the Aufbau principle. Can I speak German in here? That's my minor. All right, so we have this. Lowest amount of energy is going to be associated with electrons in the 1s level, since they're closest to the nucleus. The farther away we go, the more energy we get. So let's build. From 1s, we go to 2s. Now, 2s, we go to 2p, but realize these are the same distance away. This is the second main energy level. It's just this is a further confined shape within the second energy level. Notice, though, that the p's are a little bit higher energy level than the s's. Okay? I can't remember what I've said in this class versus the other class. We already talked about relative energies of S versus P versus D versus F, which one's more energetic. Well, if we did, I'll remind you anyway. But what you're going to see is that the more, like I told you before when I was talking about the shapes, I think, the more you confine this shape, the more you restrict those electrons, the more energy they're going to hold. So that means, since P is sort of a more specific confined shape than S, anything in P is going to have more energy. The electrons will have more energy than the electrons in S at any given time. Just like D would have more than P, and F would have more than all of them. Okay? But realize that when we go to 3S, for example, still anything in the third level is going to have more energy than anything in the second or the first level. The S's, P's, and D's only become important whenever you're looking within the same level as that, at 2 different electrons. Okay? So like if you're looking at 3S and 2P, this actually has more energy. 3s would have more energy than any of the 2p electrons. 3p would have more than 3s. Okay? 2p would have more than 2s, but still, even though this is an s, 3s would have more than 2p. Okay? All right, but I want to point out something here that gets a little screwy. This all works perfectly as we continue to build. But what happens, and this is where this happens, is right about the transition metal block on the periodic table. You'll see what I'm talking about when we start going through this. But remember I told you like charges were unpredictable and you couldn't just assume anything. You had to figure it out. And you're going to see why. But when you start arranging up and get about this high, so notice how many electrons we're dealing with. 2, 4, 6, 8, 10, 12, 14, 16, 18. When we get to somewhere around 20-some electrons, it gets a little, we take a sort of a different step. It sort of changes a little bit on us. Because what you'll see is that 3D, that's a pretty big orbital, actually. There's 10 electrons that could occupy this particular shape. When we get into what's called the D block on the table, when we get into elements that start involving D as part of their electron configuration, there seems to be a little bit of instability associated with them. You get a lot of electron movement between orbitals. Things are pretty tight right through here in terms of things bouncing around. So what you get is a situation where actually 4s, even though it's a higher energy level up, 4s actually has less energy than what 3d has. Okay. You'll also see that when you go from 4p to 4d, 5s actually has more energy than 4p, which makes sense, but it actually has less energy than 4d. So you've got these d orbitals that sort of have an extra amount of energy than what they're supposed to have, and that gives you a lot of the properties that you see when it comes to transition metals, how they're kind of screwy, and the things that they can do. Anyways, because it's not perfect like this, there's a specific way that we have to learn to remember how these stack on top of each other. I'm going to show you an easy way to do that. When we do fill these orbitals, you got to keep a few things in mind. Okay, something called the Pauli exclusion principle. We've already talked about it. We just gave it a name now. Each orbital can only hold 2 electrons, right? The s can hold 2. Each p shape can hold 2 for a total of 6. That's what this is saying. That's called, actually has a name. Pauli exclusion principle is what that's called. Also, what you need to realize is that when electrons, they have been found that they spin around. It's sort of like they're like a tiny, I hate to say this because I don't want you to give the wrong impression, but imagine like a tiny little planet that spins on its axis. Since it is matter, but yet it is energy. In its matter form, it seems that there's this oscillation, there's this spinning around, this tiny little electron. And when an electron spins like it has an axis, it creates a magnetic field. So what you have to do is to keep everything from falling apart and from matter ceasing to exist. What has to happen is when these electrons occupy the same orbital, like if there's both of them are in s, you'll find that one of them has to spin this way. And if the other one spun the same way, can't do that very well. If the other one spun the same way, they would contribute and further and propagate the same magnetic potential, and it would spiral out of control. There would be too much magnetic field there. So what has to happen is if this one's spinning this way, the other one has to spin in the opposite direction. Is that right? The other one has to spin in the opposite direction, okay, to cancel each other out. It's sort of like when you're in the swimming pool, and there's like 2 or 3 people in it. Say you're in like a little above ground pool or something, and everybody gets to the side, and you stay along the edge, and you keep walking around and like get the water to swirl. The only way you can, the more people you get going the same direction, the more of an effect you get. But if you walk the other way and get just as many people walking the other way, you can cancel it out, right? It sort of just ends up with no effect. Sort of the same principle here. You got to spin in one way. Whatever one else is joining it in that orbital has to spin the opposite way to maintain, I don't know what, keep everything together, keep chaos from ensuing. So that's why I say opposite spins, so the magnetic field will cancel. So, for example, if you see what's called orbital diagrams, this just shows boxes showing you what electrons are occupying what orbital that we're building. So if you have a blank box, nothing's in there, when you add one, generally orbital diagram means you use an arrow to represent an electron. And the whole point is just so you can point things in different directions. So that, this means one electron's there. It doesn't matter if you start up or down. It doesn't really matter. Just realize that if you put another electron in there, you usually visualize it and show that by pointing the arrow in the other direction so that you express the fact that you know that these electrons are spinning in opposite directions. Okay. So let's take a look at some elements here. Hydrogen is up there. Hydrogen has an electron configuration known as 1s, right? That means it has one main energy level. If you look at the periodic table, look at hydrogen. It's the very first element. How many protons does it have? 1. That's all hydrogen is a proton. There's not even any neutrons. It's got 1 proton in its ground state, when everything's happy and perfect. How many electrons does it have? 1, right? It has to balance out the protons. However, well, we'll get to that in a minute, but hydrogen is 1s, so we can say 1s1. It has 1 electron in the first main energy level, the 1s level. All right, let's look at helium. Notice the only difference between helium and hydrogen in terms of electrons. Now, there's obviously a difference in protons, right? There's 1 more proton. That's what makes it helium. But let's look at its electrons. Notice that it's the same, everything that you had with hydrogen plus another electron. If you look at helium on the table, it's number 2. It has atomic number of 2. It has 2 protons. So in its ground state, it should have 2 electrons, right? So instead of being 1s1, it should be 1s2. Look at lithium, you're going to see a pattern here, right, as we go down through the table. Lithium has 3 protons. In a ground state, it should have 3 electrons to cancel that out, to make it stable. So if you're going to make 3 electrons, realize that now you've already filled the 1s, right? It's full. It's got 2 of them. The next place you put your next electron is whatever else. We don't have any P's or D's or F's in the one level. Remember I said that every level only has, whatever main level you're in, that's how many subshells you can use. Okay, so like with the first level, there's only 1, the S. With the second level, there's S and P. With the third, there's SPD. Fourth, SPDF. And then after that, you can keep doing SPDF. Okay? So if we're building up, and we have 1 S2 already, that was helium, and we need 1 more, we have to add in the 2S level, and we just put 1 electron in there. We don't have to fill it if we don't need to. That just tells us how many it can hold. All right, so lithium would be 1s2, 2s1. That would be its configuration. That tells me a lot about lithium. If I were to draw an orbital diagram, look how this differs. Okay, it's really easy. There's the box. I can fit 2 in a box. There's the 1s box. I point the arrows in opposite directions. I've got helium instead of hydrogen. With lithium, I'd have that 1s box already full. I'd have to put another box for 2s, and I would just put 1 electron in it. Notice that I still have space for 1 more. That's where beryllium comes in. It would be atomic number 4. It could have 4 electrons, right, in its ground state. So we went from 1s to 1s2, 1s2, 2s1, 1s2, 2s2. Okay, it makes logical sense the way that we're working through this. You follow me on this? All right. We can continue going all the way down, but I want you to notice something here. When we get into the 2p level, pay attention right here especially. Take a look at boron and carbon. Boron has 5 electrons. So we can go 1s2, 2s2, all the way up to 2p6 if we needed to. But we didn't need to because it only has 5 electrons. So when we get to 1s2, 2s2 like this, it was only 4 electrons. Okay, I need 1 more. So the next step is to 2p. Okay? When I get to 2p, I actually draw 3 boxes because I know that there are 3 separate shapes that make up that p. So, bam, bam, bam. I start filling them in. Okay, easy enough. When I go to carbon, carbon has 6 protons, thus in its ground state would have 6 electrons in its configuration. 1s2, 2s2, 2p1. I'll have all of that again, but another one for 2p2. But notice how I've added that in the orbital diagram. I did not double up on that and fill it first. What I want to do is go in and fill in all the boxes first and then come back and double up. Okay? Now, the reason is because that's what electrons want to do. Just keep in mind that electrons want to achieve the lowest energetic state possible. So just like us, if there's 3 places to go, and there's 3 of us, if there's 3 different rooms in one house, and there's 3 of us, and we go in, it'd be just weird if we all decided to stay in the same room together, right? I mean, we all want our space. If given the opportunity to maintain the lowest energy and the most sanity, we spread out, okay? Or like this, I've been thinking of that Seinfeld episode. I don't know why I just thought of that, but like the close talker, you know? Right? Like those people who just get right up and get like this far away when they're talking to you. It's like you just want to slap them. Give me some space, man. Anyways, electrons are going to spread out within that energy level so as to keep the lowest amount of energy, and then only when they have to, like when you see here, when you add 1 more, now realize you've still got 3 more electrons this can hold, right? But when it adds up, it's going to go back. You don't know which one. Technically, it doesn't matter when you start to double up, where you start to double up, because there's no way of knowing what these boxes actually represent, which orbital it's going to be. That doesn't matter. Just realize you can only double up after they're full, though. You can only start doubling up. Carbon's very interesting. I'll come back to that in a second. There's something special about carbon and what you see up there that you probably don't pick up on yet. So you can see where it just continues. We build on the previous elements over and over until we get to like neon. Okay, I want you to notice something about neon, though. In its outermost energy level, how many electrons do you see? The outermost energy level is the 2nd energy level, right? That involves both the S and the P in this case. How many do you see? You see 8. Okay. 6 of them are in the P, 2 of them are in the S, but altogether that makes 8. Okay. Come back to that. All right. So here's how you write. Here's how you remember the order. Because remember, it changes a little bit, like in the 4S 3D kind of thing. So here's an easy way to remember this, and I will not give you this on the test. You'll have to come up with this yourself. So I'm going to show you how to draw this. This is called the order of fill chart, the order in which electrons fill in. Follow the arrows. I'm going to let it run by itself, and then I'll walk you through it. Okay, so pay attention to what it's getting ready to do. But first, before we fill it in, know how to draw this. Here's the easiest way to draw it. Okay, there's some numbers missing, but I'm going to let you go ahead and write the numbers in because it's easier to remember that way. You'll want to start and write 1 through 7. Like imagine lined paper, and on each line write 1, and then 2, and then 3 until you get to 7. Then go to the next a column over. Do the same thing, except don't start with number 1, only start with number 2 on the second line down. Do the same thing. You can even write in this 7 here that's not there. It doesn't matter. Go over to the next line. Start with 3, do the same thing. Go to the next line or column and start with 4 and do the same thing. So what you should have then is sort of like a triangle thing that you've drawn here on your paper. You have a column of 7, same column that starts with 2, same column that starts with 3, same column that starts with 4. Well, there's 4 columns, right? We have 4 different sublevels that exist, S, P, D, and F. Make the first one, write S's after all the first one. Write P's, D's for these guys, F's for those guys. Easy enough? Okay, you'll have to memorize that. I'm not going to give that to you again. All right, here's how it works. Follow it. It's what we fill first. Then we fill that one. And it comes back from 2P to 3S. So far, so good. 3P, but notice instead of going to 3D, it goes to 4S first. Wraps back around. It repeats itself this way. So if you're going to draw this out, make sure you draw it nicely so that everything is in line and you don't get confused. This is the order of fill. You're going to go from 1S to 2S. Come back around. 2S to 2P to 3S. Come back around. There to there. Come back around. 3D, 4P, 5S. Notice how it gets crazy here. Come back around. 4D, 5P, 6S. The more farther it goes down here, the crazier it gets. But you can go ahead and leave those things. Like if you wanted to draw this 7 here, we'll never use it, but it's not going to hurt it to draw it on there if that's how you have to memorize it, like how to draw this whole chart. That's okay. Does that make sense to you, how we do this? Okay, so if I'm asking you to write the electron configuration, all you need to know is how many electrons something has. Once you know how many electrons you need, you use this, because you know that for every S, you can hold how many electrons? Every P is 6, every D is 10, every F is 14. So if you have 3 electrons, what's the electron configuration? 1s2, 2s1. What if you got 5 electrons? Bingo. Okay, that's how we fill it. That's a lot easier than trying to draw this out in your head and make all these 3-dimensional models. Okay. All right. We already talked about this, so I'm going to go ahead and skip over this. But whenever I mentioned a while ago in those little boxes, orbital diagrams, whenever I said you fill all, like if you're in the 2P, you fill each block before you go back and double up. That actually has a name. It's called Hund's rule. Okay, that's saying that before they make pairs, they're going to divvy it all out, and they're all going to fill one box in like a P shell or a D or whatever. They're all going to spread out before they ever start doubling up. Okay. So let's take a look at this. Here's krypton. You look at the periodic table, and I asked you to deduce the electron configuration, how the electrons in krypton are arranged. It's actually pretty simple to do. You've got everything you need to know. It has 36 electrons according to its ground state. If you look it up, you'll see it's number 36. That means it has 36 protons, 36 electrons in the ground state, when everything's occupied like it's supposed to be. Okay, if that were true, then you could follow your order of fill chart and come up with that as your electron configuration. Okay? Follow it. 1s2. When you get to 1s, you know that you can fit 2 in there. Go to 2s. How many can you fit in there? 2. Then what's next? And you keep tracing your way through, all the while keeping track of those exponents because that's the number of electrons that you are using. Once you reach 36, once your exponents add up to 36, you're done. Okay? That's the electron configuration. All right. Look at krypton. What is your outermost energy level? What level? N equals what? 4. I said the level. I'm not asking for electrons. I just want the farthest level that you go out is the 4th level. Right? So how many valence electrons are there? How many electrons are present in the outermost energy level? 8. What do you know about krypton? What group does it belong to? It's a noble gas. Huh. Okay. See some recurring patterns here. Now, there is an abbreviated way to write this. Now, right now, it's not going to save you that much time, but very shortly, I'll show you how it will. There is a way to take all of this, and instead of writing all of this out, write it in a much shorter form. It's called a noble gas configuration. Notice this. Okay? Here's the thing about noble gases. Noble gases are useful to us as a reference point because noble gases typically don't fluctuate, they don't change, they don't react with things. So their ground state, the way their electrons are arranged, changes very little. Okay? So we can use it as a reference point. We can compare other things to them because they change, they're so unreactive. Realize that in chemical reactions, that's what's changing, these electrons and where they are. Notice here, see all this in green? That's the same thing as the green that you see up here. Okay? This, what you see, this whole thing, including the 5s1, is rubidium. If you looked at rubidium on the periodic table, since we read from left to right, if you find krypton, go to the next element in sequence, you will find that it's rubidium. It's all the way in group 1. It's 1 square past krypton. That means it has 1 more proton, right? And it also has 1 more electron in the ground state. So it should make sense then, if that is true, that when you're writing the electron configuration for rubidium, it should be exactly like krypton, but with 1 more electron, right? So that's what you have. You have exactly like krypton, but 5s1 for that 1 more electron. Okay? Now, because all of this is exactly like krypton, we instead can collapse all of this into an abbreviation that is just the elemental abbreviation of krypton. Okay? So what this tells me, if I use this abbreviation, it means the electron configuration of rubidium is whatever's krypton is plus 5s1. Okay? I call that the noble gas configuration. Now, I realize that since we're just learning how to do this, that doesn't seem much like an abbreviation for you because you have to write all that out to even find out if it's the same. Right? But I'll show you a way a little bit later as to how this becomes a very useful tool. Okay. Now, realize that when you're writing a noble gas configuration, well, I'll show you that one on the table. I won't say that now. I'll show you. Okay. Let's take magnesium. I want you to, here's your problem. I want you to give me an orbital diagram and electron configuration of magnesium. Okay. I think it's easier for me to come up with an electron configuration and then give an orbital diagram. But for the sake of doing what the book does, let's do an orbital diagram first and then give an electron configuration. Magnesium has 12 protons, so when it's ground state, it's going to have 12 electrons, right? So what we'll do is start drawing boxes. You don't have to use them all. Just start drawing the ones that you know in the order that you know, right? Take your order of fill chart and draw a 1s. That's going to be 1 box. Draw another box for 2s. Next is 2p. That's actually going to be 3 boxes, right? Because there's 3 separate shapes inside that p. So that will be your 2p. Next is your 3s. That's what comes next. After 3s is 3p. So you draw those boxes. Now you'd stop and look and say, okay, I know magnesium has how many electrons we dealing with? 12. Only 2 can go in each box, right? So I've probably got more than what I need. I just got to check and look. 2, 4, 6, 8, 10, 12. I gave it a couple extra just in case I need them, so I don't need to draw any more boxes. I'll just leave it like this. Okay? Now it's a matter of filling these in. This is the order that they go in. The only difference here between electron configurations and orbital diagrams just tell you, point out the whole electron spin and the whole one spread out versus double up thing. That's the only real difference between what we're doing here and just writing it out with numbers and letters. So if you've got 12, then we know to do this, right? I'm going to fill these up. Those are going to spread out. I'm counting them. Now I'm going to go back and double up before I move to the next level. Okay, I don't need any more. You see how that worked? So I've got 12 electrons I've got to account for. I can fit 2 of them in here with opposite spins. Then I move on, 2 of them in here with opposite spins. Now I'm going to go up, up, up first. Then I'll go back and go down, down, down if I need to. And that's what I did. I've got 2, 4, 6, 8, 10 electrons. I still got 2 more I got to put in here. They both can fit in 3s, 1 up, 1 down, opposite spins. I don't even need these. Okay. All right. So there's my orbital diagram. Just like that, with the boxes and the arrows for magnesium. To write the configuration, I can get the configuration very easily from the orbital diagram, just by looking at it if I draw it out. If I don't ask you to draw it, just use the order of field chart. Put it in. You know that it's going to be 1s is where you're going to start. That'll hold 2. Next in line is 2s. That'll hold 2. Next comes 2p. That'll hold 6. Now we're up to 6, 8, 10. I need 2 more, so I got to go to the next one. That's 3s, and that can hold both of the 2 that I need. So there it is. 1s2, 2s2, 2p6, 3s2. That is the electron configuration for magnesium. Now, notice on your table, right before magnesium, what's the noble gas right before magnesium? Neon, obviously. If you just look here, you can figure it out. If you count and look at the electron configuration for magnesium, you'll see that it's 1s2, 2s2, 2p6. Here's an easy way to count. Just count the electrons, right? Magnesium is neon is number 10, right? So it should have 10 electrons in its ground state. 6, 8, 10, right? Those 10 electrons right there, organized in that fashion, represent neon. So I put neon in brackets, and I could write whatever's behind it, right? 3s2. So there's the electron configuration. Here's the noble gas configuration. There's the orbital diagram for electrons and magnesium. Questions about that? One in parentheses. The only thing that you can put in here is noble gases. That's it. And the reason is because they're the only ones whose configurations don't change from situation to situation. They are stable, they're unreactive, they're a reference point that never changes. So we can only use them. And also, as you're getting ready to find out, that's what everything wants to be like. All of the atoms on the periodic table will react in a manner so as to try their best to become exactly like whatever noble gas is closest to them in terms of their electron. Not unless I ask for it. You just have to know how to do it. Depends on what I ask. If I don't specify, then you can do that however you want. It doesn't matter to me what you do as long as you understand what you're doing. Okay. All right, valence electrons. I mentioned this already in lab, right? Those are the ones that, or whatever electrons are associated with the outermost energy level. And we care about those because those are the ones that are going to be involved with bonding. Whenever you stick something next to each other, what's called the core electrons. The core electrons are the ones below the valence electrons, inside. They're never going to get to interact with other electrons from other places, really. What we care most about are the ones on the very outside and how many of them there are. That determines how many things it'll react with at any given time and what it will react with. Okay? So we've got valence versus core electrons. Know the difference between those. Okay? So the chemical and physical properties of something has everything, absolutely everything to do with the number of valence electrons that it possesses. Okay? I want to point out a couple things here as we get in with this. Let's go back to rubidium. Here is our configuration for rubidium. Remind me, look up here, don't cheat. Remind me again, I can abbreviate this, right? What would I abbreviate that with? You just look on the table and see what's right in front of rubidium, and it's krypton, right? So krypton 5s1 is another way to write this. The long way is this way. Okay? When you add up all those exponents, you should get 37. Okay. Notice what it says. If I asked you how many valence electrons rubidium has, the answer is 1. Because the highest level present is 5, and it has 1 electron in that 5th level. Look at krypton. point this out again. It's everything that was green up here, right? Here's krypton. Notice it. Its highest level is the 4th level. It has 8 electrons. Huh? The S and the P, you got to add them together. It's not there. Well, the D is associated. The D is there, but it's in the 3rd level, not the 4th level. What we're looking at is only the things in the 4th level. Those are the ones farthest out. The 3D is here because it fills before this one fills. But that doesn't mean that it's the farthest out. All this represents is the order that they fill in. The big numbers actually represent how far away they are from the nucleus. Okay? All right. Notice in this case, to point it out again, we've got 8 valence electrons. This is a recurring pattern with the noble gases. All of them have 8 valence electrons when you write their configuration. The next one down after krypton would be 5s2, 5p6. And then the next one would be 6s2, 6p6 when you wrote it out, and so on. But they all add up to have 8 in their outer shell, with the exception of one, which is helium. It only has 2. Okay? So I want you to notice that. This periodic table is a little bit different. I want you to pay attention to what I've done here. I've skipped over the entire transition metal block. Right? We go straight from lithium to beryllium in the top left. Then there's that big space right above the transition metals. And then you start in with boron on the right side. That's what we've done here. So we've just kind of cut out the middle part and crammed it all together. Notice something. Okay? If you write the electron configuration for hydrogen, 1s1. Helium, 1s2. Keep going. Lithium, 1s2. It's everything there. This just tells you what it ends with. Okay? If it ends at 2s1, beneath it you have to have a 1s2. Right? Beryllium. The configuration is 1s2, 2s2. Right? It's got everything that it had beneath it. It did this. That's there too. Now it kicked up to here. It went all the way to here. What you see here is the very last one that would be written. Okay? Notice this. Whenever I write these, look at all the alkali metals, including hydrogen, even though it's not a metal. This is why hydrogen even behaves like all these metals here, and why all these metals behave like each other. They all have how many valence electrons? 1. They all have 1 valence electron. What charge do they like to form? Remember? Positive 1. There's got to be a correlation there. What do you think it is? Might want to take a guess before we get too far into it. Exactly. Get that? I told you that everything is trying to be like the noble gas that's closest to it. Take a look at lithium, for example. What's the closest noble gas to lithium? Helium. How many valence electrons does helium have? 2. How many does lithium have? If you can imagine this lithium existing right in front of you, it's got a 1s that's got 2 of them in there, right? On top of that, it's got a 2s with 1 of them in there. If I could take that 2s1, make it disappear, how many valence electrons would lithium have? It would have 2, because the shell underneath has 2 in it, right? So what lithium likes to do is get rid of that 2s1 electron, because just beneath it, it can expose this and create a 1s2 situation, making it exactly like helium. That's what it wants to do. That's what it strives to do. That's why it performs the reactions and participates in the things that it does. Notice that sodium will do the exact same thing. It is bigger than lithium, right? There are more electrons here, more protons, but nevertheless, it still ends in an S1. It still has on the third level out just 1 valence electron. Beneath that, there is a 2s2, 2p6 right below it, just like neon. So what sodium will do is try to get rid of that, so it can be like the noble gas that was closest to it, in this case neon. It's not going to try to be like argon. That's too much work. It has to gain too much stuff. It's easier to lose 1 than it is to try to gain 7 to be like argon. Okay? Whichever one it's closest to. So it makes sense that things that are right here, they're only 1 block away from a noble gas. Things that are right here are only 1 block away from a noble gas. They can taste it. They're almost there. How do you think the reactivity compares, these guys compared to things in the middle? What do you think? Are these and these guys more or less reactive than the guys down here? I've heard both. Why do you think it's more? Why would these guys be more? Well, they've got a lot less of a distance to go, right? That's an unfair question to ask. You don't really know. One really knows why. But these guys are definitely, your halogens are going to be much more reactive. These are reactive gases. Think about it. Bromine, chlorine, these are toxic things. Remember what I told you, everything about sodium and potassium. You know, they're dangerous. You throw them in water, they explode. You're not even supposed to touch them. Whereas things like this, I mean, carbon, that makes us up. We have carbon all through us all the time. Nitrogen we breathe in. Oxygen we even breathe in. You don't breathe in fluorine. You don't breathe in chlorine. There's a reason. These things are very reactive. They're so close to being where they want to be, it doesn't take much to get them there. Okay? So this starts to make a little more sense now in terms of the periodic table. You can look at this stuff. Notice the noble gases. 2s2, 2p6. Next one down, 3s2, 3p6. The next one down is going to be 4s2, 4p6. The only deviation from that is just helium because there's not enough electrons to make 8, right? So there's something special about the 2. Now, interestingly, we don't know what it is about the 8. We don't know what it is about that 2 that makes it so happy. All that we can really say is that's what we observe, and that's what everything seems to be trying to do. It's the best explanation that we have. There's the way that the energy is distributed when you have 8 valence electrons on the outside. Whatever it is about the energies, when considering all the electrons below it in the core, the way that it spaces out is a special distribution, sort of a magic set of energy dispersal to where everything seems to be happy and unreactive. It's a lowest energy form that seems to be achievable. So that's why everything is striving to do that. So if I asked you, why does fluorine form a 1 negative charge? What would you tell me? If I told you that you had to memorize that fluorine and chlorine, whatever, they always have a negative 1 charge. Why? They want to add an electron. Explain further. So what happens once they add an electron to try to become like a noble gas? What happens to the ground state situation? Instead of being balanced, they now have 1 more electron than they do protons. Exactly. So that offsets it, and that makes it a negative 1 charge, right? Think back in terms of these guys in the group 1. They have 1 valence electron. What happens when they lose their 1? Now you don't have a balance in ground state that you had with positives and negatives in terms of protons and electrons. By losing an electron, you now have 1 more proton than what you have electrons, so you get a positive charge. That's how you get charges. That's where all those charges come from on the periodic table. It all has to do with this movement of electrons. Okay? Pretty neat stuff. Okay. So what you should have noticed is that, let me go back here. Notice this. As we go up and down through the columns, remember we call these groups or families, right, on the periodic table? As we go down, what we should notice is things in the same family or the same group have the same number of valence electrons. Okay? Things in the same period or row going across, what do you notice about them? Okay, they get bigger. What do you mean by that? What do you notice happening? Yes, they have the same amount of energy levels, right? Someone said they get bigger, and that's right, because you add more energy levels. Here you're in the second main level, right? Then we go to the third main level, and the fourth, and then we go down to the fourth and the fifth. We keep increasing. So notice in dual what is happening here. We've got, every time we go down, we're getting more energy levels. Every time we go across, we're just adding electrons within that energy level, right? And as we go across and look at the columns as we go across, since we are adding them one at a time, it makes sense that every column then should be just 1 level bigger than the other one. They should match in terms of the valence electrons that you see. Okay. I never thought the periodic table had so much meaning. Just think of how organized, how much work it took to organize the table like it is. You see it, don't think much about it, but everything that we've learned so far, charges, which are related to this, all the numbers on it, the size, the masses, how everything lines up perfectly. The hardest thing imaginable would be to line it up according to what we see here. Okay? And all of that went in and just make the table shape that it's in. That's why you should be like me. You should go get a shower curtain that is a table of elements. It will make you happy, and every time you go to bathe or shower, you can appreciate all that's around you every time you look at it. And then let me know if you want to get like what I have too. I have little like 7 or 8 boxes of elements that have different samples of natural forms of these elements and hang them on the wall. So what else I want to do? I want to get a family portrait, but the portrait's going to be our DNA. I'm going to cut it with the same restriction enzyme, and blot it out, have the gel, take a picture of it, blow it up, have like an 8x10 frame of like my DNA sequence, put my name on the bottom, and do my wife's and then my kids. Family portrait, put it all in. I thought it was cool. I'm a dork, so. All right, so you should have recognized these trends. It makes sense then that as we look here at the periodic table, notice a couple things here. Okay, the color coding scheme, number 1. Number 2, which we already said. Notice how all of these guys right here all have the same number of valence electrons, right? They just go to a higher energy level to do that. As we go across, we are adding electrons, and they have the same number of valence electrons. Now, you can see where it gets real screwy right around in here. Don't fret too much about that. We're not going to focus on that too much. Just know that you can still follow the rules that I have to do what you need to do for this class. Notice that we have broken the table down further into what's called the S block, the D block, the P block, and the F block. Okay? What that means is when you're dealing with like valence and you're dealing with where these things end, this is going to end in S's, right? This would sort of end in a D. It's the only place you're going to use the D's, is basically what this means too. Transition metals is the only time you're really going to use these D's. The P block, as you can see, you got an ending in P over here. You'll see that pattern repeating. Down here is where the F's come into play. Okay? It's very separated. It's very organized. How does this benefit you? Notice I put an X through helium because technically what should happen, if you're ever looking at a table like this, that's why sometimes when you look at periodic tables, sometimes the helium is detached. The reason that the helium is, well, sometimes the hydrogen is too. The reason the hydrogen gets detached is because it's not a metal, and it wants to point out the fact that you realize that it's not connected to the metals. It just sort of behaves like the metals. Okay? Helium is sometimes detached because it doesn't fit into the P block, because it doesn't have enough electrons to fit in the P block. But yet it behaves like the noble gases, so it gets separated out. But this one, I just wanted to point that out. All right. Now, this is where it's going to be very beneficial for the noble gas configuration. When we recognize what we just saw, and we notice a repeating pattern, we can come up with what's called a noble gas configuration. It's actually pretty easy to do. Now, the previous slide explains all this. I'm just going to walk it through on the picture. Let's say, for example, I wanted you to give me the electron configuration for phosphorus so that you could tell me how many valence electrons it has. Well, you could probably guess how many valence electrons it has. How many valence electrons do the halogens have? 7, so it makes sense that these guys probably have 6, right? And these guys probably have 5. So that's reasonable, but say I want you to prove it to me. I want you to show it to me. So you could write out the electron configuration. That would, it's a little bit more work, but certainly doable at this point. Or you could just use what you know about how the periodic table is stacked up on itself and take a shortcut by using noble gas configurations. Show you what I mean. If I want to show you I want you to show me the configuration for phosphorus, what you would do is start with the noble gas that's just previous phosphorus. You can't use the one after it, obviously, because it's going to have more electrons than what phosphorus is going to have. So we got to go back one. So we'll start with neon here. So write neon in brackets. And what you're telling me is that encompasses all of the electrons that you see up to neon, and including neon. Okay? So you write neon in brackets. Then we use the SPDF block thing to our advantage. For example, I go from neon, I go over one more square. That means it would be neon 3s1. If I go here, it will be neon 3s2. See what I'm doing? Then I skip all the way across. I stay in the same row. This would be 3p. right? 3p1, 3p2, 3p3. Notice how this works out, 5, 6, right, before you get to noble gases. Notice in the S's, how many columns is there? 2. 2 electrons in the S, right? There should be 10 right through here because D holds 10. Notice how many go across there? 14, right? There's a lot of organization here. So if I want to write the electron configuration for phosphorus, one way I could do that is just write neon in brackets and then count my way across using the table. I know that I'm in the third level now. This is the S's. This would be S1. This would be S2. Okay? Well, I filled up to 3s2, so I had to write 3s2, right? I have to write that down. So now I'm into the 3p's. I could write 3p1, but I will go past that. I go to 3p2. I land on 3p3, so I would write neon 3s2, since it's filled up 3s2, and going over to 1, 2, 3, 3p3. Does that make sense? See how I did that? So the configuration for phosphorus would be neon 3s2, 3p3. If I had, what's next? Let's do a different one. Let's do sulfur. Sulfur is right here. Okay? If sulfur was right here, what would be the configuration of sulfur? Noble gas configuration. Good. Neon 3s2, 3p4. There's a noble gas configuration for, what did I just say? Sulfur. Okay? Chlorine would be one more over. 3p5, right? So it's pretty simple. It's pretty straightforward. Okay, there is one catch, though. The nice thing about using noble gas configurations, too, though, is it very easily makes it noticeable in terms of valence electrons because it sort of kicks them out to the side without having to think too much about it. That's what ends up being left over. But anyways, let's do arsenic. If I want you to write the noble gas configuration for arsenic. Now this is, I choose this on purpose because there's a little bit of an exception here. Oops. Now watch what happens. I'm going to go to the noble gas before it, right? I'll write down argon. I got to kick it back over, so I made it to 4s2. Uh-oh. I had to cross the D block. Okay? Before I could get through the P. So I want to point something out here if it looks confusing. Remember order of fill. It still applies. You go from 1s2 to 2s2 to 2p6 to 3s2, right? From 3s2, 3p6, whatever. You just keep building. If you follow that progression, you will notice that the 4s fills before the 3d. Don't make the mistake of, since you're in the fourth level, realize the only exception to what we're talking about here, which is good, there's only one exception this time, is when we get to the D block, this transition metal block right here, the D actually is going to be in the level that's one below where you're at right now. So in other words, 4s2, 3d, in this case 10, you cross all 10, then back to 4 again, 4p, 3. Okay? Your D is always one level behind where you are as you are going. Just keep that in mind. So for arsenic, you would write argon, 4s2, since we crossed both the blocks in the S. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We cross all 10 of the D blocks, so we write 3d10. Now we're back to 4 again. 1, 2, 3, the third block over, 4p3. This is a lot faster way to do it. It's a lot easier way to count up instead of writing everything out. If I don't tell you anything, and I just want you to count valence electrons, stuff like that, you're welcome to do it any way you want. But if I specifically ask for longhand notation or I specifically ask for noble gas, you've got to be able to do both. So don't just learn one of them. Okay, so how many valence electrons? Well, I guess I told you on there. I was going to ask you how many valence electrons arsenic has after you write it. Well, we went from, so it's argon, and then we write 4s2, 3d10, 4p3. How many valence electrons you have? You want to look at the electrons in the outermost energy level. Notice that you have 5. Okay, it's 3 away from being happy, being like the next noble gas. Okay, I mentioned already about how important these valence electrons are. Things that have the same number of valence electrons, they tend to behave the same. So if you take a look at noble gases, for example, notice that they all have 8. There's something special about that. Most of them are completely unreactive, especially these first two, almost considered inert, as if they, like no reaction at all. Sometimes you can elicit reactions out of some of these heavier ones if you work really hard at it, set up unnatural conditions, that kind of stuff. But pretty much they're just stable the way they are. Radon, of course, though, is radioactive. It doesn't react with anything, but it in itself, the nucleus starts to sort of decay sometimes, and it gives off energy when it does that. It's radiation. Okay. Notice that helium only has 2. Okay. By the way, it made me think when I saw argon. That's how we learn about a light being released when electrons jump through different levels, right? We know that if it drops from a higher energy to a lower energy, light is emitted. Well, the emission spectra for argon actually is almost like white light. Matter of fact, it's the color you see. These are argon-filled tubes and fluorescent tubes. And what you have is an electric current that passes through, and there's a little blob of mercury. It's vaporized really easy, right? Because mercury is pretty stable, but it's a metal. But it happens to be a liquid metal at temperature. So what will happen is when the current goes through, that's why it's sort of got a bluish twinge too, because mercury sort of has a bluish color. There's only a little bit of a blue. It's like a bluer white than what white is. It's not blue. It's just, if you can imagine diluting just a tad of blue in your white, pure white light, you get something sort of like this. That mercury gets vaporized, and then the energy that's in that mercury gets dissipated out to all the floating argon that's around. Now, argon is unreactive, virtually unreactive. But what can happen is that energy can be absorbed by the argon atoms, and then those electrons kick up into their higher orbits, and then they fall back down very quickly. And when they do, they emit an emission spectrum that's very close to, well, white light. But there is a different color, right? It's not pure white light. If you've been around fluorescent lights enough, you know that it's not the same as like a light bulb, right? But that's how these things work. That's why if you ever drop one, they explode. They got gas inside. It's argon gas inside these fluorescent light bulbs. But it's all about quantum mechanics. It's all about electrons absorbing energy, falling back down in the orbital in the shells, and then those atoms emit an energy. That's why it takes a minute when you flip on a switch. When you have an incandescent light bulb with a filament, the second you flip the switch, bam, you got light. When you have a fluorescent light, there's a little bit of a delay, right? Because what has to happen is that electricity gets transmitted to that mercury. That mercury has to be vaporized, and that energy has to be dissipated out through argon. It's not just an electric current. It's actual energy transfer between molecules. So it takes a little bit. And also takes a little bit to shut off, too, but nowhere near as it does to get going. Neat stuff. All right. Take a look at, like I said, everybody wants to be like a noble gas. So consider your alkali metals. Notice all of the valence electrons. They're all going to want to lose that outside electron in order to be like the noble gas just previous to them. And when they do, they end up with a 1 positive charge because now they have an offset imbalance of protons and electrons. Same thing for halogens. If we go over to the other side, they've got 7. They want to gain 1. When they do, you get an extra electron present that wasn't there before, so you have a -1 charge. That's why now, if you put sodium next to chlorine, you're going to get a reaction. If it's pure sodium, like elemental sodium, put that block of sodium inside chlorine gas and let them go. Realize that they are both very reactive because sodium really wants to give up that electron to be like neon. Is that what's in front of it? And then chlorine really wants to gain that 1 electron to be like the noble gas that's just in front of it. So they're a match made in heaven. Okay, ready to go. I've already mentioned all those. This is just showing you that when we go from sodium, realize that this is the electron configuration for sodium, but the reason that sodium forms a positive charge is because it wants to get rid of that electron. Because when it gets rid of that electron, now it looks like neon. It's not neon. You're not going to confuse a sodium ion with neon. If you look at these two things side by side, you will notice that there's an obvious difference in the number of neutrons and protons that are present. So it's easy to identify the atom. However, what is the same between them is their electronic structure, how their electrons are arranged now. Okay? It's not like it becomes neon. It's just it takes its electrons and stacks them in a way that's exactly like neons. That's all it's saying. Same number of electrons as neon. But it's still sodium because we haven't changed the number of protons. That's all this chart shows. Okay, let me point out a couple things here. I'm going to skip over this and explain it as I show you the picture. It makes sense that as we as we go down the table, we add more energy levels, right? We get bigger and bigger and bigger. It makes sense that the size of the atom continues to increase. Because when we talk about atomic size, we're talking about the distance from the center of the nucleus all the way to the very outside electron. Okay, that's the radius that we're talking about here. So obviously, the farther down we go, you can see that these guys are much bigger than like hydrogen and helium. Makes sense. However, how does this work? Because take a look at level 4. Notice I have potassium here. I have krypton here. Why wouldn't they all be the same size since they're all in the 4th main energy level? Well, it has to do with every time we go from this block to this, like to another block, like when we go from here to here, we add another electron, but what else do we add? We don't really add it, but what else is the difference between it? What is there one more of when we go from here to here? What is the difference between potassium and calcium? By definition, what makes them two different elements? Number of protons. When I go from here to here, I don't just add an electron. I add a proton. And I add a proton and an electron. I add a proton and an electron, proton and electron. Every time I add more protons and electrons, without increasing the distance that they are away, I increase the attraction for the nucleus to the electrons flying around it. It's almost like the gravity potential gets bigger and bigger, and it sucks them in a little bit farther. Okay, do you see what I mean if you think about that? The distance of the electrons around this potassium is only n equals 4. It only goes out to the 4th level. Just like this one only goes out to the 4th level. However, the difference is, in that 4th level, there's a whole lot more electrons and a whole lot more protons in that same amount of space over here than there is over here. So that means there's more positive-negative attraction going on. There's more density, more like gravitational pull almost by the atom. It's not really like it is, but you can imagine it. And it sort of pulls everything in a little bit tighter. So that means as you go down, yes, everything gets bigger. But as you go across, it actually gets smaller. Okay? So it's sort of like if we start here and work ourselves diagonally across the table all the way down, that's how things get bigger. Okay? The best way to write this is not the way that's on that particular chart. Let me show you a better way, what you might want to write down. Is take this bottom one down here and make your arrow point towards cesium, towards the left. Then go down here on the left side and draw an arrow going down. So that they meet sort of at the same point. Okay? Because what that tells us is the farther we go that way and the farther we go down, so as we go this way, the bigger it gets, the bigger the atom gets. Okay? So you can see, for example, that argon is smaller than chlorine. It's also smaller, though, than krypton. Okay, so we'll take a look at this stuff. So let's look at an example. I explained this already, but if you consider Group 2A, Group 2, the alkali earth metals, you've got beryllium, magnesium, and calcium. Okay, they're right on top of each other on the periodic table. What is the difference between them? Notice that as you go down, obviously, you go to a different energy level, right? So this one's going to have 4 main energy levels. That one's only going to have 3. Above that, that one's only going to have 2. So obviously, this atom is going to be much bigger than that one, and that one's going to be bigger than that one. Okay, that's pretty easy to deduce. However, let's look at a period as we go across. Let's look at lithium, and then right next to it's beryllium. So we're in the 2nd main energy level. Lithium, beryllium, and then boron is over on the other side, but same level. Or you can do the same thing with carbon, oxygen, and neon. Notice that all of them only have 2 energy levels. Okay, but the difference is you keep adding protons each time. And this distance starts to shrink because there's more attraction, because you're adding more stuff. Okay? So that's why we see that trend. As we, as we move from top to bottom, things get bigger. But as we move from left to right, things get smaller. Okay? So drawing the arrows like I showed you shows an increase. It increases from right to left, and it also increases from top to bottom. That's why I had those arrows drawn on the side to meet, like I showed you. Ignore that. We don't even need that. So let me ask you. Take a look. Don't cheat. See if you can figure it out. Carbon or oxygen, which one's going to be bigger? Carbon. Okay? To the left. Lithium or potassium? Potassium. It's below it. Carbon or aluminum? Aluminum. Remember, we're down and to the left is bigger. What about selenium or iodine? You can't tell. They could be the same size. They're probably going to be very close. If you want to tell the difference in size, which one, you're going to have to do more analysis than what we can predict with this table. There's some other things you have to consider. So if I give you something like that are side by side, you can't tell which one's down and to the left, you can't answer it. You just say, I can't tell. All right. Another one is what's called ionization energy. Ionization energy is how much energy it takes to knock an electron loose from one of these atoms. You'll notice that some of these atoms really hang on to their electrons. Okay? It takes a lot of energy for you to bam them, put it into them in order to dislodge those electrons and send them flying. Other ones are very loose with their electrons. They don't value them as much as they should, or as much as they could. So it doesn't take much energy to jostle them loose a little bit and send those electrons flying. This is called ionization energy. Okay? Now remember, we're talking about electrons in the valence shell because it's going to be way too hard to dislodge core electrons. The ones that are exposed are on the very outside. That's what we're going to be messing with here. So, take what you know about sodium and chlorine. Which one do you think it's easier to remove an electron from? Chlorine or sodium? Why is it easier to remove it from sodium, do you think? Yeah, think about what we've just talked about, right? How many valence does it have? It has one. It wants to give it up anyways, right? You'll find that sodium has a lower ionization energy than chlorine. It requires less energy to dislodge its electron than does chlorine require. Okay? All right, now realize that you could do this more than once. Okay? If I have I'm talking about gaseous form, by the way. It's how much, you have to have some relative point. What ionization energy actually means is how much energy does it take if I had the gaseous version of the substance. Okay? So whatever element I have in gaseous form, if I put in energy into it, it's endothermic. That means I have to put energy into whatever's happening. I can dislodge an electron, right? Well, I can take that cation that I have left, put some more energy into it, do a second ionization energy, and dislodge another electron. And I can, in theory, keep going. But realize that the farther down we go and the more we ionize, the harder it gets to dislodge these things. The first one's always the easiest to dislodge. Then as we keep going and try to ionize the rest of it further, it gets a little more difficult because we're dealing with higher energy situation, or more stable, I guess, situation. Okay. Now, what you will find is there's also a pattern on the table that we can use to predict ionization energy. It says right here, as the atomic radius increases, so in other words, as the atom gets bigger and bigger and bigger, right, it requires less ionization energy. Just imagine, it's like any empire that gets too big, it gets too hard to control, right? If you have an atom and it starts just accumulating these electrons, it's much, much harder for it to keep those electrons under control and to hold them in. So what tends to happen is your bigger atoms that have a whole bunch of electrons are the easiest to ionize, the easiest ones to cause them to get dislodged from. That's one reason that things like uranium are used for what they're used for. Obviously, that's a nuclear process, and it's the neutrons that are become important. But things like that certainly can have electrons dislodged very easily as well. Okay, stay with me. I'm just going to finish this slide. So what that means is the same thing almost. Since it has to do everything with size, this is just a reverse of the thing I just showed you, right? Because the biggest one's down here, right? This is the biggest one. That means it has the lowest amount of ionization energy. It takes the least amount of effort to dislodge its electron. So that would mean the opposite is true if I'm talking about high ionization energy. The things that require a whole lot of energy go just the opposite. Instead of going this way, they go this way. So fluorine, for example, takes a lot of energy to dislodge the electrons from fluorine. It takes very little energy to dislodge the electrons from francium. Okay? So that's trends in ionization energy, how much energy it takes to knock electrons loose. You don't need to know this part of that. What I just said. Skip this. Okay, so Answer this for me. The highest ionization energy right here, magnesium or phosphorus? Which one has the highest amount of, which one would it take more energy to dislodge its electrons from? Phosphorus. AS or SB, which one? Okay, arsenic. Nitrogen or silicon? Nitrogen. It's above and to the right. Then I've got oxygen or chlorine. You can't tell on that. They're sort of diagonally side by side. Not from what just normal prediction. We can't tell. It takes about the same amount of energy, roughly close, to dislodge electrons from those two elements.